Up to now in our discussion of strategic interaction among small numbers of firms, we've been talking about models of homogeneous products. So mostly we've talked about the duopoly model where two firms produce an identical product, but there are just the two firms, and so we still had to think about each firm making its choice in light of what the other was doing. Now we're still in a world that's like that, but now what's going to happen is we're going to have differentiated products. So we'll still have duopoly, but now, as I say, it's differentiated products duopoly. So what does that mean? Well, it means importantly that now price is a strategic variable. In the homogeneous product context, firms only decided how much to produce, and the decisions of each of them of how much to produce gave rise to the total output, which in turn determined the price along the demand curve. But with differentiated products, firms have some ability to control their own pricing. And for example, they could raise their price a bit without losing all their demand. I mean, think about the example of Coke and Pepsi. And ask yourself, can you tell them apart? And certainly based on my own experience, I could tell you most people have a preference of one for the other. Many of the people who say they have a preference can, in fact, tell them apart. And I guess most importantly, from our standpoint, the people who prefer one over the other will stick, say, with Coke, even if the price of Pepsi falls or the price of Coke rises a bit. There is some substitutability. Some people will switch from one to the other, with any price difference. But some people would remain loyal to the product they prefer, even as the price goes up a bit. And that's the hallmark of differentiated products that are imperfect substitutes. Let's think about yogurt too, since we have talked about yogurt and our Dannon and Yoplait examples earlier. For example, what happens to the quantity of Yoplait sold when its price changes, or when the price of the rival product, the Dannon price, changes? It turns out, if you analyze the data, again, the data that we've seen earlier in the course, you'll see that the quantity of Yoplait sold depends negatively on the price of Yoplait. That's no surprise. If the price of Yoplait goes up, the quantity of Yoplait demanded goes down. That's just the regular old demand curve. But what's also true is that as the price of Dannon goes up, the quantity of Yoplait sold goes up. Now, why is that? That's because as the price of Dannon goes up, some of the consumers leave Dannon and go over to Yoplait because they're substitutes. Not perfect substitutes, but substitutes. And similarly, if you look at the quantity of Dannon that gets sold, it bears a negative relationship to the price of Dannon. Again, that's just the demand curve that slopes downward for one's own product. But now, when the price of Yoplait goes up, we see that the quantity of Dannon sold goes up. So in summing up, how much I sell depends both on my price and on yours. And what I want to think about here is a model of this, but a model of this in particular where there are just two players with differentiated products. And so we can call this the differentiated products oligopoly model, but in particular we'll be focusing on two firms. So we could say it's duopoly. So we're thinking about two firms that sell goods that are imperfect substitutes. Now let's consider the following example. It's a lot like the Dannon and Yoplait example we just entertained, except that the numbers are simplified a bit so that things are symmetric. So what are we saying? The quantity of product 1 sold equals 100 minus 3 times the price of product 1 plus 2 times the price of product 2. The quantity of product 2 sold equals 100 minus 3 times the price of product 2 plus 2 times the price of product 1. And to keep this simple, frankly, it's going to get pretty complicated anyways, but to not add additional complication, let's say that the marginal costs and fixed costs are all 0. Now, what do these demand functions mean? We've really already said that. We're just saying that as my own product rises, the quantity I sell falls. As the other product's price rises, it causes people to come over to my product. So as the other product's price rises, the quantity I sell rises. Now, what are we after here? Let me step back and give a little bit of a big picture story, then we'll jump into an analytical model. But what we want to find is my best price. So now the strategic variable is price as opposed to quantity. And I want to find the best price I should charge. It's going to turn out, however, that the best price for me to charge will depend in part on the price that the other product is being sold for. And so if you think about it, that means my best price is not simply an answer, it's not a number 6 or something, it's a relationship between what you're charging and what I should charge, which means that we're in the world of reaction curves. I'm going to have a function showing the best thing I should do as a function of what you're doing, and you'll have a function showing the best thing you should do, and best meaning best price you should charge, as a function of what price I'm charging. And so we'll want to think about where those intersect. All right, that's big picture, but let's talk small picture and work through the model. So what have we got here? Profit is just P1, so profit for firm 1, I should say, is just P1 times Q1. There are no costs, so revenue is profit. Now, if we substitute for Q1, this expression that involves P1 and P2, we have that profit for firm 1 equals P1 times the quantity 100 minus 3P1 plus 2P2. And again, what we're looking for is the best P1 to charge given the price P2 that's being charged, and that's going to be a price reaction curve. Now, in order to get there, we need to find firm 1's marginal revenue. Now, what's different is that, typically we've calculated marginal revenue where the marginal idea is what happens to revenue if we change the quantity by 1. Here we're talking about a marginal revenue with respect to price, so it's a little bit different. Still, though, we can use the same sorts of tools. So let's write the demand curve for firm 1 in the following way. Q1 equals, let's call it an intercept, 100 plus 2P2, minus something involving its own strategic variable, minus 3 times P1. Now, all I've done here is I've rewritten the demand curve. Now, we need to get the marginal revenue, and so let's use the bisecting idea. Marginal revenue has the same intercept as demand, but it has twice the slope, so we'll multiply that 3P1 by 2. Then we need to set MR1 equal to MC, and MC is 0, so this is MR for firm 1 equals 0. If we solve it for P1, what we've got is firm 1's reaction curve. Now it's interesting just to stare at this for a second. Remember in the homogeneous goods case, when we found a reaction curve there, it was showed the best Q1 as a function of Q2. And there, the more you produced, the less I ideally wanted to produce. So there was a negative relationship between your quantity and my quantity along my reaction curve. Here it's the opposite. Notice that P1 equals 16.67 plus 1/3 times P2. That says the higher is your price, the higher I want to set my price. And that makes a lot of sense. The higher is your price, the more it is that your price choice is stimulating my demand. So you having a higher price makes me want to have a higher price. All right, well, let's continue on. We've set this problem up symmetrically, and that helps a little bit, but firm 2 also has a reaction curve. We want to find it. And because of the symmetry, and what do I mean by symmetry? Let's just think back to the demand curves we wrote down a few slides ago. They were the same, except we just switched the subscripts. The coefficients were the same, but the subscripts were different. So it really is a symmetric problem. That means we end up with a firm 2 reaction curve that looks like this. And we can plug P2 in for, well, P2 in firm 1's reaction curve, and we end up with an equation here that only involves P1. It's a little bit ugly, but if we solve it through a few steps of, sort of tedious algebra, we end up with P1 equals 25. And similarly, if we were to solve it through, we'd find that P2 equals 25. Well, this is a big deal. So we just found that the equilibrium, it's kind of like a Nash equilibrium in prices, and we're going to call this a Bertrand equilibrium for historical reasons, but we're going to end up with prices of 25 for each of the two firms. And what are we doing graphically? Well, here I'm just showing the reaction functions for the two firms. So for example, this blue one is firm 1's reaction curve. P1 is 16.67 or 100 over 6 plus 1/3 times P2. So the higher is P2 along this axis, the higher is optimal P1 along this axis. And firm 2's reaction curve is drawn in green. And where they cross is the price of 25 for each firm. Now let's think about how the firms do in this Bertrand equilibrium. So first of all, we know their prices are 25, so they each have a price of 25. What about the quantities? Well, think about, Q1, it was equal to 100 minus 3 times P1 plus 2 times P2. And so that's what we're doing here, although we're noticing that there's symmetry. But let's just think about it as Q1 for a second. So Q1 equals 100 minus 3 times 25 plus 2 times 25. So that's 100 minus 75 plus 50, or 75. So that means each of the firms produces 75 units of its output. How about profit? Well, profit is the same as revenue here because there are no costs. So we've got a price of 25 times a quantity of 75 equals a revenue and profit in this instance of 1875. So each of the firms earns 1875 in profit. All right, let's use this juncture as a juncture for taking stock. And what are the takeaways thus far? Well, the first thing is that with differentiated products oligopoly, and in our instance it's literally been duopoly, my best price depends on yours. All right, this is a world of strategic interaction with large players, so what you do affects what's good for me, which means that we're kind of intertwined in this strategic sense. A second point, and it's more kind of tactical about solving problems, I find my price reaction curve by bisecting the demand curve when written in terms of prices. And then we find the equilibrium by solving the reaction curves together to get the Bertrand solution. And it's very analogous to how we did the Nash-Cournot equilibrium in quantities.